Hello, and thank you for joining in. I'm Marian Menning, Development Engineer at IAV's Commercial Vehicle Powertrain Department, and today I will present to you an internal research study on the comparison of hydrogen and diesel propulsion systems for on-highway commercial vehicle applications. The agenda for this presentation starts off with the enablers for alternative powertrain systems. We show the scenarios we see for on-road heavy-duty vehicles by the year of 2030. The main topic of this presentation is to show you our methodology in using GT tools to compare these scenarios. After that, we give you a brief look at our results, give an outlook for non-road mobile machineries, and close the presentation with a summary. The enabler for alternative powertrain structures for on-road commercial vehicles are CO2 and emission regulations. In the EU, the CO2 regulations currently in place demand a CO2 fleet reduction from 2019 to 2030 by 30%. In addition, there's a requirement for trucks to have at least 2% of low and zero emission vehicles in each fleet. The further tightening of emission regulation, especially the Euro 7 discussions and the ultra-NOx phases, are also an important driver. The most important vehicle classes are 4, 5, 9 and 10, as they are responsible for the highest share in total CO2 emissions. The EU classes are shown in the lower right corner. 4 and 5 are 16-ton 2-axle vehicles, and 9 and 10 cover vehicles with 3 axles at every weight. The zero and low emission goals don't stop on the road. There are policies and drivers for non-road mobile machineries as well. Fuel and CO2 reduction are also the main drivers. However, we see a minor pressure by legislations in the time frame up to 2030. With no global non-road mobile machinery CO2 regulation in place, we still see a push in alternative powertrains. Countries like Norway with zero-emission construction sites are drivers. We already see a ramp up of electrified construction equipment. Back to the on-highway applications. We need a basis of comparison for possible propulsion systems. With vector methodology for calculating vehicle-specific CO2 values, the EU has the goal to monitor CO2 on a fleet level. It's a map-based approach to calculate the efficiency of engine, drivetrain, rolling resistance, and air resistance. It also will include electric vehicles and hybrid vehicles in the future. We decided to use Vector as a reference because of the importance in the EU with respect to the CO2 regulations. Vector offers drive cycles, these are well known, and offer us the baseline to interpret and validate our results. Next, we will look at the scenarios we see for heavy-duty long-haul applications. On this slide, we see our scenarios for long-haul heavy-duty applications. For fuel types, we have identified diesel and hydrogen. Pure battery electrical vehicles in this class are likely, but not for standard long-haul applications. The powertrain structures will still include diesel with further efficiency improvements, and hydrogen as a combustion engine, and hydrogen as a fuel cell with an electrical drive. Comparing and benchmarking these powertrains, diesel, hydrogen, combustion engine, battery electric, and fuel cell electric, is a challenging and complex task. Thanks to the capabilities of GT ISE, we were able to set up a platform model to cover multiple propulsion variants. With our methodology we share with you today, we can reduce cost, time, and effort in the developing process. How we did that will be the part of the next section, in which I will show you our simulation methodology. GT ISE offers the possibility to include component models as submodules, and you can easily switch these submodules in the case setup. So we were able to include all these powertrain variants in one platform model by switching our component models. For example, we can switch from a combustion engine